Imagine for a moment you're trying to tune into your favorite radio station, maybe driving home, but someone intentionally is just scrambling the signal. It's all static.
Yeah.
Or perhaps even weirder, they're somehow tricking your device, your phone maybe, into thinking a channel is completely jammed when it's actually wide open, ready for use. That is not just annoying static or some minor glitch. It's actually a critical challenge. It strikes right at the heart of how our
whole modern wireless world operates.
Indeed. It really does. The invisible highways, our electromagnetic spectrum, they're just getting more and more crowded.
Definitely.
Cybersecurity threat within these dynamic networks, what's known as the Byzantine attack.
Ah, yes, the Byzantine generals problem, but for radio waves.
Kind of, yeah. Our mission is to unpack precisely how malicious users try to fool these wireless systems, and maybe more importantly, reveal a powerful and actually surprisingly elegant new way to detect them and even neutralize them.
And our journey today really centers on an advanced machine learning technique. It's known as Gaussian Mixture Models, or GMMs.
GMMs, okay.
And this isn't just about spotting some rogue
signal like a blip on a radar. It's more about understanding the subtle statistical fingerprint of deception.
A fingerprint. I like that.
And then leveraging that insight to protect our wireless.
Which often leads to these vast, underutilized sections of airwaves. It's just a huge inefficiency, isn't it? Like having a giant parking lot where most spots are reserved, but, half the time they're empty.
That's a perfect analogy. Huge inefficiency.
Yeah.
And cognitive radio, or CR, that steps in as a truly innovative solution to exactly that inefficiency. It's designed to dynamically allocate spectrum.
Dynamically, okay.
So it allows unlicensed users, we usually call them secondary users, or SUs, to legally
Find and use these spectrum holes.
Spectrum holes, like those empty parking spots.
Exactly like the empty parking spots. They're essentially unused frequency bands within the licensed spectrum.
This is the core mechanism for identifying those valuable spectrum holes. These secondary users, the SUs, they must accurately detect the presence or absence of the primary user. So they know precisely when it's safe for them to transmit and, maybe even more critically, when they absolutely must stand down to avoid causing that interference.
What happens when some of these secondary users aren't playing fair?
Yeah. Twist.
What if they're deliberately trying to distort that crucial sensing information?
Trying to, mess with the system.
So our mission today for this deep dive is to explore exactly how these malicious users, MUs we can call them,
machine learning solution.
The GMM approach.
The GMM approach, yeah. That not only precisely identifies these attackers, but can actually even mitigate their harmful impact, ensure our wireless communications stay robust, efficient, and, importantly, trustworthy.
So by the end of this deep dive, you, our listeners, should gain a really comprehensive understanding of the core mechanics. Cognitive radio, cooperative spectrum sensing.
Foundation.
You'll grasp the insidious nature of these Byzantine attacks, why some of the, let's say,
traditional defenses often fall short, and how this particular GMM-based anomaly detection algorithm offers a superior, much more adaptive defense.
day without even thinking about it.
Absolutely, it's a hidden battlefield.
So let's unpack this. Let's dive in. Let's kick things off by setting the scene properly. This ever-expanding wireless frontier and the hidden vulnerabilities that inevitably come with it.
Right.
We are, it's undeniable, living in an era of truly insatiable demand for wireless communication.
This is everywhere.
Just think about it.
Yeah.
Every device in your pocket, every smart appliance in your home, the streaming services you use constantly, the burgeoning Internet of Things.
Billions of devices.
Even these nascent smart cities forming around us, they all rely on wireless signals, and this exponential rise means our electromagnetic spectrum, which is, fundamentally finite.
It's a colossal inefficiency. Think of it like a vast library where most books just sit on the shelf, perfectly organized, maybe, but never checked out.
Or back to the parking lot. Thousands of empty spaces nobody can use because they're technically reserved, even if the owner is miles away.
Exactly. That's the inefficiency static allocation creates.
And that's exactly where cognitive radio, CR, steps in as a truly brilliant and frankly necessary solution.
It really is.
This technology is specifically designed to dynamically allocate
Spectrum, allowing those unlicensed users or secondary users or SUs to legally jump onto licensed frequencies.
Opportunistically.
Yes, opportunistic.
Function effectively for it to really realize its promise is what we call spectrum sensing.
right. Sensing first.
It's the fundamental process,
Yeah.
accurately identifying those spectrum holes. Secondary users have to precisely detect the presence, or, just as importantly, the absence of primary users.
Okay.
This knowledge dictates when it's safe for them to transmit, and critically, when they absolutely must stand down and vacate the channel. Immediately.
Let's just quickly revisit that parking lot analogy again, because I think it helps.
That's a good one.
Under static allocation, each car has a reserved spot.
Whether it's there or not, lots of empty but technically occupied spaces.
Right.
Cognitive radio is like a smart system. It lets other cars temporarily use those empty reserve.
Chaos.
Total chaos. Okay, so sensing is key. But doing it alone as a single user has problems.
Now, while single-user spectrum sensing is sort of the foundational concept, relying on just one user alone has significant limitations. It suffers from common wireless channel ailments that can severely degrade that sensing accuracy.
Yeah, these are the usual suspects of wireless comms, right? The environmental things that mess with signals like path loss.
Path loss, exactly. Signal strength just naturally drops off significantly over distance.
Makes distant PUs really hard to detect.
Okay. And then there's fading.
Fading, yeah.
Right.
Those unpredictable, often rapid fluctuations in signal strength caused by multipath propagation.
For the signal is super weak or just non-existent.
So, path loss, fading, shadowing, all making it hard for one little SU to know what's really going on.
Precisely. All these issues significantly degrade a single secondary user's ability to accurately sense the spectrum. Imagine trying to hear a faint whisper across a very noisy, crowded room,
Okay.
while also dealing with echoes that sometimes make the sound louder or softer, and people walking directly in front of you momentarily blocking the sound entirely.
Yeah, that sounds impossible.
It's incredibly difficult to get a clear, consistent signal or make a reliable decision in those kinds of conditions.
So to kind of collectively overcome these nasty effects and build a more
central entity, the Fusion Center, or FDC.
The Fusion Center's role is absolutely critical here. It's the conductor of the orchestra.
Yay, yeah, I like that.
It acts as the ultimate decision maker, synthesizing all that incoming information. It takes all the individual reports from the various SUs and applies some kind of sophisticated fusion rule.
A rule to combine the inputs intelligently?
Right, to make a final, much more robust, much more reliable decision on the primary user status. Are they really present or really absent?
Okay.
And only then,
With this aggregated, more accurate picture, does it dictate channel access to the secondary users.
So it's like your noisy room example, multiple people listen, compare notes.
While cooperative spectrum sensing significantly improves reliability by leveraging collaboration, its very strength, its open, cooperative nature is also potentially its greatest vulnerability.
It's a classic paradox, isn't it?
Yeah. Precisely what makes CSS so strong, this reliance on shared information can also be its greatest weakness.
That's the Achilles heel right there.
Yeah.
In an open, collaborative environment where trust is kind of implicitly assumed,
You have to trust the other sensors, yeah.
Some users might intentionally provide false or misleading information to the Fusion Center. These are our malicious users, our Byzantine attackers.
Okay.
And the attack itself is generally known.
HSUs, okay. Honest ones.
and the Fusion Center itself. And they can be pretty clever, pursuing both goals simultaneously to maximize their, let's call it, attack utility.
So, what are the two main goals?
Okay, first goal, cause a false alarm.
False alarm, like shouting fire when there isn't one.
Exactly like that. This is where they trick the honest SUs into believing a primary user channel is occupied when it's actually completely free.
Okay, and the impact.
Well, this causes the honest users to miss valuable spectrum opportunities.
It essentially locks them out of an available, clean channel, reduces network efficiency for everyone else, hurts the whole point of CR.
Right. Keeps them from using the empty parking spot. Okay, what's this?
Secondary users to inadvertently interfere with the licensed primary user.
Which could cause real problems.
Huge problems. Potentially severe regulatory issues, hefty fines for the network operator, maybe even widespread network disruption for critical services using that license band. It's like whispering, all clear, when there's a real fire leading others right into danger.
Wow, okay. So it's abundantly clear then. Identifying and then somehow either eliminating or neutralizing these Byzantine attackers is absolutely essential.
Non-negotiable.
For the continued success, reliability,
And, regulatory compliance of any cognitive radio network using CSS.
Absolutely.
Which brings us back to that fundamental question that echoes through all of network security.
can give us an unexpected edge in unmasking these digital deceivers. But first, maybe we should talk about the limitations of existing approaches. Why do we need something like GMM? Why isn't this already solved?
Good point. A lot of the early work in CSS, especially concerning defenses against these malicious users, focus on what's called hard combining.
Hard combining. What does that mean?
It means the secondary users, after doing their local sensing, report a simple binary decision to the fusion center. Just a 1, meaning PU present, or a 0, meaning PU absent.
A simple yes, no.
Very simple. Yes, no. However, this research and what we're digging into today focuses on soft combining.
Soft combining. Okay, difference.
Here, the SUUs report
More detail.
Exactly. That granular detail, that continuous stream of information, is precisely what advanced machine learning techniques like GMM can really sink their teeth into. It lets them spot the subtle statistical deceptions much more effectively.
Makes sense. More data, more patterns to find.
Precisely. And it's not like researchers haven't explored machine learning for defense before. There have definitely been efforts.
Like what?
Well, using algorithms like one class support vector machines, SVMs, for MU detection, or linear and
nonlinear SVMs for trying to detect the PU's boundaries. We've also seen k-nearest neighbor, KNN, algorithms being used for attacker detection.
Okay.
And even more complex combinations.
particularly the supervised learning algorithms, require labeled data sets.
Meaning you need to know who's bad before you train the model.
Exactly. In a constantly changing, really dynamic cognitive radio environment, getting consistently labeled data, knowing exactly who is malicious and who is honest at any given moment, is incredibly difficult, maybe impossible in real time.
Yeah, that seems like a showstopper for deployment.
It's a huge hurdle. Another significant limitation lies in how some of these algorithms actually model the data. Algorithms like SVM and C-means clustering, they tend to form circular clusters
when they group data.
Circular clusters, like perfect circles.
Yes, mathematically speaking. And this is where it gets really interesting, because real-world data distributions in CR networks
The data looks like, I don't know, scattered clouds or overlapping amoebas.
Yeah.
But the algorithm can only draw perfect circles. It's going to miss a lot of the nuance, isn't it? It's forcing a shape onto the data that isn't there.
Exactly. You've hit the nail on the head. And finally, one more big one. Many of these existing ML algorithms, including SVM and C-means, are computationally very expensive.
Meaning they need a lot of processing power over time.
Both, usually. This severely limits their practical use in real-time CR networks, where decisions about who can access the spectrum and
who might be a threat need to be made almost instantaneously, like within milliseconds.
Okay, so challenges are need for unsupervised learning, no labels, complex data shapes, not...
circular clusters of Gaussian distributed data.
Gaussian distributed, like bell curves.
Exactly, bell curves. The Gaussian mixture model is inherently a soft clustering approach. It doesn't force hard boundaries. And it's perfectly suited for precisely these kinds of distributions because it models the data as a combination of multiple Gaussian or bell curve distributions.
A mixture of Gaussians, hence the name.
Hence the name. This makes it an ideal fit for accurately modeling this complex data and, crucially, identifying subtle anomalies or outliers within it, which is exactly what we need to spot the MUs.
Okay, so let's dive into what a Gaussian mixture model actually is. You said it's an unsupervised machine learning algorithm, primarily used for clustering. For our listeners, what is that?
core idea is that GMM assumes the data it's given comes from a mixture of several underlying Gaussian distributions, several bell curves mixed together.
Right.
It then sets about figuring out the parameters of these individual Gaussian distributions. It needs to find their central point, the mean.
Where the peak of the bell curve is?
The spread of variance, how wide the bell curve is,
Okay.
and how much each component contributes to the overall data set, their weight. It tries to find
The combination of these individual bell curves that best represents the underlying data structure.
So it's like it's looking at a lumpy data set and saying, okay, I think this lumpiness is actually made up of...
Well, you usually tell it how many components, how many bell curves. Look for like K2 in our case, but yes, the rest is spot on. It's discovering the distinct groups hidden within the data.
Gotcha.
And in this specific context, since the data we're dealing with, those energy values reported by the SUs is one-dimensional, it's just a single measurement.
Just a number.
A univariate GMM model is used, which simplifies the modeling down to just a single variable. Mathematically, the overall probability of observing any given data point, any energy value x, is described as
A weighted sum of these individual Gaussian functions. Each Gaussian J has its own weight, its own mean reg, and its own variance Jeff.
Okay, mathematically, it's a sum of weighted bell curve.
without any supervision, without labels.
Iterative. Meaning it tries, checks how well it did, refines its guess, tries again over and over.
Precisely. It refines its guesses repeatedly, getting closer to the best fit each time. It starts with step 1, initialization.
Okay.
The parameters, the means, variances, and weights of the Gaussian distributions it's looking for are randomly or sometimes heuristically initialized. These are essentially the algorithm's first, maybe rough guesses about where the bell curves might be.
Just a starting point.
Just a starting point.
Uh-huh.
Then we move to the heart of the process, which alternates between two crucial steps. E and M.
E&M, expectation and maximization.
Exactly.
Yeah, so a data point might have, say, an 80% probability of belonging to Gaussian A and a 20% probability of belonging to Gaussian B, based on the model's current guesses. It's a soft assignment, not a hard, you belong here.
Okay, probabilistic assignment. That's the E step. What's the M step?
Then in step 3, the M step, or maximization step, the algorithm re-estimates all the parameters, the means, variances, and weights based on those responsibilities calculated in the E step.
Using the probabilities to update the guesses.
Exactly. It's
Essentially, updating the positions, means, spreads, variances, and sizes of the bell curves to better fit the data. Now it has a clearer probabilistic assignment of points to each curve.
until step 4, convergence. The algorithm iterates between the E and M steps until either the log likelihood function, which is a measure of how well the model fits the data overall, or the parameter values themselves show negligible change between iterations.
So until the model stabilizes and isn't really improving anymore.
Right. That indicates it has found a stable set of parameters that best describe the data's underlying mixture of Gaussian distributions.
And what about that
Problem of local maxima you mentioned earlier, getting stuck on a small hill instead of the highest mountain. How does EM handle that?
That's a very good analogy, and it's a real issue. The likelihood function can indeed
For the parameters.
Okay, so we're starting from different places on the So you run it maybe 10 times, pick the best result.
Something like that, yes. This significantly increases the chance of finding the global optimum, the true best fit for the data. Makes the whole process much more robust for real-world applications.
Okay, that makes a lot of sense. Now that we really understand GMM and its EM engine, let's connect it back directly to our core problem.
Detecting those sneaky, malicious users. Tell us about the proposed GMM-based anomaly detection algorithm. How does it use this GMM framework?
Okay, the key...
Because of this inherent duality, the GMM is specifically fitted with K2. We tell it to look for two Gaussian probability density functions, two bell curves, to model these two fundamental states reflected in the energy levels reported by the SUs.
So it's basically trying to learn the normal energy patterns for both an empty channel and an occupied channel simultaneously, creating two distinct models of expected behavior from the data.
Precisely. Once the GMM is successfully trained on the
aggregated data from all the secondary users, honest and malicious mixed together, it can then compute the likelihood or density for each individual data point that it processes later on. Or
then identified as anomalies or outliers. They simply don't fit the expected normal patterns very well according to the model.
Okay, so the core logic seems simple. If a data point doesn't fit the learned normal patterns, the two bell curves representing empty and occupied channels, it gets flagged as an anomaly. Makes sense. But how does that directly tell us who the malicious users are? Because you hinted at this counterintuitive part. A lower anomaly count flags them as malicious. Why on earth would attackers
have fewer anomalies? That seems backwards.
That's the fascinating paradox, isn't it? And it's absolutely critical to understand this inverse logic. Think about honest users first.
Okay.
Level of anomalies just due to reflecting reality.
Okay, so honest data is a bit noisy, has some natural outliers. Makes sense.
But think about the malicious users. What are they trying to do?
They're trying to deceive the fusion center. Right. Either make a free channel look busy, false alarm, or a busy channel look free, misdetection.
Exactly. And how do they do that in the soft attack model? They sense the energy, and if it's, say, too low for a false alarm attack, they add a specific amount DOE. If it's too high for a misdetection attack,
they subtract. They are actively manipulating their reports to push them towards what they think the fusion center expects for the opposite state.
Ah, so they're trying to make their lie look like the truth of the...
Precisely. They are trying to make their falsified reports fall within the bounds of what they perceive as normal for the state they're trying to mimic. In doing so, they are artificially suppressing the natural variability and the occasional legitimate outliers that an honest user reporting that same state would exhibit. They're essentially ironing out the natural wrinkles in the data.
So by trying to be deceptively normal according to the wrong state, they end up looking abnormally normal overall, like too smooth, too consistent.
You've got it. Their efforts to appear average, to blend in perfectly with the state they're faking, make them unnaturally precise compared to the honest users whose data reflects the noisy reality.
That's really clever. So the GMM, trained mostly on the honest users' slightly messy data, learns a model of normal that includes some natural noise and outliers. The malicious users, in trying to be perfectly deceptive, generate data that's too clean, too close to the center of their fake target, and therefore produces fewer points that the GMM considers anomalous.
Exactly. Though too good to be true, reports lack reflects the statistical signature of honest noise and variation. And that difference in the number of anomalies generated per user
becomes the detection signal. A lower anomaly count flags them as suspicious.
That makes so much more sense now. It's like they're trying to hit the bullseye every single time, even when real-world conditions...
Step 1. Reshape dataset. First, you take all the collected data, remember it's from p-sensing instances and M cooperative secondary users, giving us a PXM dataset, like a spreadsheet. This gets reshaped into one single, long L/1 training vector, where L is just M times P. We just stack all the readings into one big column.
Okay, flatten the data. Got it.
Step 2. For GMM, K2. Then we train our Gaussian Mixture Model on this long vector. As we discussed, we set K2 because we have two hypotheses, PU absent, A0,
and PU present, H1. The expectation maximization algorithm runs its iterative process to find the optimal parameters, the means, variances, joy, and weights J.
Step 3. Compute density. Right. Now, with the GMM trained, and its two underlying component distributions defined, the algorithm calculates the probability density, or likelihood, for each individual energy reading in that long L/1 training vector. This value, as we said, is the GMM's assessment of how likely or normal each specific energy reading is according to the model it just learned.
How well does each point fit the combined model?
Step 4. Set density threshold. Step percent.
Okay, now we need to decide what counts as an anomaly. To do this, a density threshold is set. This is done by flagging a certain percentage, let's call it omega, of the lowest density values across the whole data set.
Step 5. Declare anomalies. Exactly. Any data points in that L/1 vector with densities lower than the percent threshold are formally declared as anomalies. These are the readings that just don't fit the established Gaussian mixture model of normal behavior very well.
Okay, now we know which readings are anomalous. How do we link that back to the users?
Step 6. Calculate a CSU anomaly count. Good question. Now, from this total pool of anomalies detected in the combined L/1 vector, the algorithm traces back.
It figures out how many of these anomalous readings originated from each individual cooperative secondary user, CSU, in the original PXM dataset. So for each user I,
C is less than a carefully determined threshold lambda.
Listen, okay. And how is OX determined? You said it wasn't just a fixed number.
Right, it's dynamic. Calculated as the minimum of two values to make it robust. The first value is LUTSU, which is computed using a clever algorithm called the OTSU algorithm. The second value provides a robust lower bound. It's set as A%, omega percent, e.g. 95% of the expected number of anomalies from honest users based on the overall anomaly rate, so that's percent of p-sensing instances. This A factor ensures we don't accidentally flag honest users who
might just be slightly less noisy than average. So OCSU, A%, A%.
Okay, so that threshold is cleverly set, using this LUTSU and a safety baseline. You mentioned the OT...
adaptive data-driven approach, which avoids needing someone to manually guess or tune a fixed threshold.
So it looks at the distribution of anomaly counts across all users and tries to find the best dividing line. That sounds very robust.
Exactly. It takes as input that vector A, which contains the anomaly counts for each individual CSU, C1, C2, CM. It then works through an iterative process. Step 1. Choose a candidate threshold. It iteratively considers each unique anomaly count value present in the vector A as a potential threshold AI. It essentially tries out every possible count value as the dividing line between
low count, potentially malicious, and high count, potentially honest.
Tries every possible split point.
Step 2, split data. For each candidate threshold AI it considers,
percentage of users in the lower group, lose a percentage in the upper group.
How big is each group?
Step 4, compute variances. Then, and this is key, it computes the variance of the anomaly counts within each of these two sets separately. Variance tells us how spread out the counts are within that group. A smaller variance means the counts in that group are clustered more tightly together.
So it measures how compact each group is for that trial threshold.
Step 5, combined variance. Exactly. It then computes a combined variance measure for the current candidate threshold AI. Typically, this is a weighted sum of the within-group
variances. The goal is to find a threshold that makes the points within each group as similar low variance as possible.
Minimize the spread within the groups it creates.
Step 6.
So it finds the split point that makes the resulting two groups, low count and high count users, internally as consistent or homogeneous as possible.
You got it. It tries to find the threshold that best minimizes the intra-class variance, making the two groups hopefully corresponding to honest versus malicious as statistically distinct from each other as possible based on their anomaly counts.
That's really smart. It automatically adapts the threshold based purely on the observed distribution of anomaly counts, making the detection much more robust
Than relying on some fixed, manually guessed number. It lets the data itself dictate the best separation point.
Exactly. It makes the algorithm much more flexible.
What does the fundamental system look like in this study?
Okay. In this work, they consider a pretty standard centralized cooperative spectrum sensing model.
Centralized meaning one main controller.
Yeah, one fusion center, there's one primary user, the PU, whose signal we're trying to detect, and then there are M cooperative secondary users, the CSUs, all collaborating to sense the presence or absence of that one PU. And all their sensing reports flow back to that single central fusion center.
Simple setup. One PU, MCSUs, one FC. And how do these CSUs
Actually hear the primary user or the lack thereof. What's the signal model they're working with?
So each CSU, let's call it CSU ENE, at any given moment N, this signals
Pretty much. However, if the primary user is indeed present, hypothesis H1, then the signal yawn is the PU's actual transmission signal seen, possibly corrupted by some channel gain high, how strongly the signal arrives at that specific CSU, plus that same ambient noise one.
So it's basically listening for either silence plus static, or the primary user's voice mixed with static, potentially at different volumes depending on the channel gain high.
That's a very good description, yes.
Okay, so that's the signal.
What assumptions are made to maybe simplify this analysis a bit? Because real-world channels are notoriously complex, right?
they are. And for analytical simplicity, and also to really
This simplifies things by assuming the PU signal arrives with the same strength at all CSUs.
Okay. Maybe less realistic, but it simplifies the math.
It does. Additionally, they sometimes assume a homogeneous network, meaning all CSUs operate in pretty similar environments, leading to comparable signal-to-noise ratios, or SNRs, across the network. Everyone hears the signal roughly equally well relative to their local noise. anomalies.
These are pretty standard simplifications in initial research like this, aren't they, to get a baseline understanding?
They are, yes. Very common.
But how do they affect the real-world
Applicability. Does this GMM approach still hold up if you take it out of this idealized lab setting?
That's an astute question and an important one. These simplifications, like
before you take it out on bumpy city roads or upsteep mountains. While the real world does have complex phenomena like fading effects, where signal strength fluctuates wildly, and varying channel gains, the fundamental principles and, importantly, the relative performance trends like GMM, significantly outperforming older methods, are expected to hold true.
So the absolute numbers might change a bit in the real world, but GMM should still be better.
That's the expectation, yes. The overall detection or mitigation performance
might be slightly lower across the board when you add fading, but the fact that GMM is a superior approach likely remains valid.
Yeah.
The core methodology's effectiveness isn't really undermined.
Measures the signal power.
Essentially, yes. This computed energy value, let's call it I, for user I, is the decision statistic, the raw data point that each CSU then reports to the fusion center.
User 1 is just the energy number.
Just the energy number. The fusion center, in turn, receives all M of these energy values, E1, E2, EM, from all the CSUs for a given sensing interval. It then computes a final aggregated diffusion statistic, TFC. In the simplest case,
the TFC is just the average of all the reported II values.
Averages all the energy readings.
Right. And this average energy TFC is then compared to a predefined threshold, tau.
Okay.
If the average energy...
subtle, and that's what makes it challenging. The paper considers a specific type called a centralized independent probabilistic small scale, or a CIPS attack.
Okay, break that down. CIPS.
Centralized means they report to a central fusion center. Independent means the malicious users operate independently of each other. They don't coordinate their lies. Probabilistic means they don't lie all the time, only with a certain probability. And small scale. Well,
that relates to the nature of the lie itself.
Which is the soft part.
Which is the soft part, exactly. It's a soft Byzantine attack. This is a particularly nuanced and difficult type of deception to detect because...
harder than just transmitting random noise or always reporting the opposite. Their attack strategy unfolds in two parts, corresponding to the two ways they can cause errors. First, for false alarm attack, relative probability. If the malicious user senses that the true energy M is below a certain internal threshold, meaning the channel looks genuinely free to them, they will occasionally increase their reported energy. They report M plus O delta instead of M. This increase happens only with the probability readings. The goal here is to push
the average energy at the FC upwards, hopefully crossing the decision threshold and misleading the FC into thinking a free channel is actually occupied.
Okay, so if it looks free, sometimes...
Conversely, for a misdetection attack, I1 probability. If the malicious user senses that the true energy M is above that same internal threshold, meaning the channel looks genuinely occupied to them, they will occasionally decrease the reported energy. They report M instead of M. This decrease happens with the probability I1. This aims to pull the average energy at the FC downwards, hopefully below the threshold, making the FC believe an occupied channel is actually free, thus
causing interference.
So if it looks busy, sometimes lie and say it's a bit weaker
Yeah.
than how much they lie by.
Exactly. A Go is the attack strength, a positive value representing how much the malicious user
This is that crucial strategic aspect of the attacker's dilemma we touched on. Right. While a very high I need so might increase their immediate success rate by causing a large shift in the reported energy, it also makes them significantly easier to detect by the fusion center or by anomaly detection algorithms like GMM.
Because the reports would just look way too different from the honest users.
Exactly. The reports would deviate too conspicuously from those of honest users, standing out like a sore thumb in the data distribution. So smart and malicious users aim for a more subtle
deception. They try to strike a delicate balance. Choose the O large enough to cause significant disruption to the CSS decision when they attack, but small enough to avoid
controlled experimentation in this domain. The simulation allows the researchers to precisely control all the parameters. The exact number of malicious users, ML, their specific attack probabilities, ML and 1, the attack strength, the primary user's activity pattern, how often A0 versus H1 occurs, the channel characteristics, like SNR. This level of granular control would be incredibly difficult, if not impossible, to achieve and replicate consistently in a real-world deployed network where so many variables are constantly changing and uncontrolled.
Lets you isolate the effect you're studying.
precisely. It allows for rigorous testing and fair comparison between different algorithms under identical, repeatable conditions. The assumption made here, which is
Well, it makes sense intuitively. If malicious users were the majority, reaching any kind of reliable consensus on the channel status through cooperation would be inherently difficult, if not impossible anyway. The whole CSS approach kind of breaks down if the bad guys outnumber the good guys significantly. So, assuming they're minorities is a practical starting point.
Okay. And how is the simulated data actually generated step by step for the experiments?
The process unfolds in a structured way for each simulation run. 1. At each sensing instance, or time slot around, all M cooperative secondary users perform their spectrum sensing using energy detection, calculating their individual local energy values based on whether the simulated PU is truly present, H1, or absent, H0, in that instance, and considering the channel noise. 2. Each CSU then reports its energy value to the simulated fusion center. This is where the attack happens. The designated malicious users
apply their soft Byzantine attack strategy, deciding whether to attack based on their sensed energy, M, and the probabilities of 0 or no one, and if they attack, reporting M plus or MO instead of M.
This ensures the final dataset contains a realistic mix of samples reflecting both channel states, allowing the GMM to learn both patterns.
So they get a good mix of H0 and H1 examples in the data.
Exactly. And if data is recorded for P total sensing instances, the final simulated dataset becomes that PXM matrix we talked about, P rows instances, by M columns users. The experiments are then carried out using this dataset, often varying parameters like the number of MUs, the attack probability, the attack strength, and the PU activity probability P to thoroughly test the GMM algorithm's robustness across a wide range of potential operating
Conditions and attack scenarios.
Okay, comprehensive simulation. That makes sense for rigorous testing. All right, let's get to the really juicy part now, the core intuition. How do these...
To really grasp this, it's important to understand the fundamental statistical nature of the energy data we're dealing with in CSS. As we mentioned, for a sufficiently large number of samples used in the energy detection process, the central limit theorem often kicks in.
The CLT makes things Gaussian.
It often does, yes. It dictates that the energy computed at each cooperative secondary user, II, can be reliably modeled as following a Gaussian distribution, a build curve.
This is a cornerstone for the GMM approach, because GMM is designed specifically for data that can be represented as a mixture of these Gaussian components.
So whether the primary user is
Precisely. The probability density function, or PDF, which describes the likelihood of observing any given energy value, will be Gaussian. Under H0, PU absent, the energy is mainly due to noise, so it will be a Gaussian with a certain mean and variance. Under H1, PU present, the energy includes the PU signal plus noise, so it will be a different Gaussian, typically with a higher mean, and possibly a different variance.
Two different bell curves representing the two states.
Right. And this is the overall decision statistic.
TSC at the fusion center is just the average of all the CSU energies, which we're modeling as Gaussian. The sum or average of Gaussian random variables is also Gaussian. So TFC itself
Okay, so that establishes the normal statistical behavior for the honest users and the overall system. Now, how do the malicious users with their soft Byzantine attacks mess this up in a way that exposes them? This is the shrinking PDF idea you mentioned, right?
Exactly. This is where it gets really interesting, and it's the core insight that makes the GMM detection work. The paper meticulously derives the mathematical form of the probability density functions for the energy values reported by the malicious users.
So what does the PDF of a letter look like?
Hey, well, it's not a simple Gaussian anymore, because the MUs only modify their values under specific conditions. For example, only add if for a false alarm.
It's distorted. And the overall PDF of the energy received from a malicious user under either H0 or H1 is a weighted sum of these various pieces, weighted by the attack probabilities NN and NO1. It's mathematically complex, but the key takeaway is how it looks compared to the honest users.
And how does it look?
It's best understood visually, as shown in the research paper's figures, particularly figure 1, which is central to their argument. When you plot the PDFs side by side, 1, the PDF from honest secondary users, H is used,
reflecting the true channel conditions, Gaussian for H0, different Gaussian for H1. 2, the derived, more complex PDF for malicious users, NOUs, reflecting their falsified reports.
Towards honest users, because the number of malicious users is assumed to be significantly less than the number of honest users MLM2. The parameters for the two Gaussian components that the GMM estimates from the combined data will naturally be biased towards the PDF of the honest users.
The GMM essentially learns what normal looks like, primarily from the honest majority, because their data dominates the training set.
Exactly. The GMM's model of normal, its estimated mixture of two Gaussians,
will closely resemble the true distributions of the honest users.
Okay, so the GMM has learned honest normal. Now, how does the MU's distorted PDF
In doing so, the overall effect on the reported energy distribution is that it effectively shrinks, or becomes more concentrated compared to the honest users distribution for the actual state they are in. They are artificially reducing the variance or spread of their own reported values.
They're making themselves look less spread out statistically.
Yes. Now remember how we carefully defined outliers or anomalies.
As samples that lie in the low probability regions of the overall GMM model, the one learned mostly from honest users.
Exactly. Outliers are points in the tails of the distribution that the GMM considers unlikely or abnormal based on the honest majority.
So where's the final connection?
Here.
Data naturally includes more points in the tails due to real-world noise and variance.
Whoa, okay, let me see if I have this. GMM learns normal plus some noise from the honest majority. MUs try to fake normalcy so well, pushing their values towards the center that they eliminate their own natural noise variance. Therefore, their too clean data produces fewer points that look like outliers, according to the GMM's model of slightly noisy reality.
You've absolutely nailed it. That's the core intuition. Their attempt to blend in makes them statistically too consistent, too central.
So the example from figure 1 in the paper actually
Shows this.
It does. It calculates the probability of a data point being declared an outlier, falling below a certain density threshold for both types of users, based on the GMM fitted to the combined.
Exactly. So what does this all mean? It means that paradoxically, by trying to blend in or deceive by aiming for normalcy, malicious users create a different, subtle statistical signature, one of too much manufactured normalcy, too little natural variation relative to the true underlying system behavior. And it's this signature, the lower production rate of anomalies, that the GMM-based algorithm cleverly detects. A lower anomaly count flags them as malicious.
That is genuinely fascinating. The
First logic is so counterintuitive at first, but it makes perfect sense when you walk through the statistics. Their camouflage is their giveaway. Incredible. Okay, so we've journeyed through the problem of Byzantine attacks.
First things first, before we even talk about detecting the attackers, what's the actual initial impact? How much damage do these malicious users cause to the basic performance of cooperative spectrum sensing?
The impact is significant, definitely not trivial. The presence of malicious users substantially degrades the detection performance of CSS.
Degrades how?
You can see it clearly when you look at the system's performance using those receiver operating characteristics, or ROC plots we mentioned. These plots show the trade-off between the probability of
Detection, Q correctly identifying an occupied channel, and the probability of false alarm, Q incorrectly flagging a free channel as occupied.
Okay, and what do the ROC...
Alarms.
Right. But then introduce just 3 malicious users into that same system, out of maybe 10 or 20 total users, attacking with moderate probability, and that QD can plummet down to 0.5, 50%.
Wow, from 80% detection down to 50%. That's huge.
It's a massive hit.
Yeah.
That represents a 36.7% reduction in the probability of correctly detecting the primary user, just due to 3 attackers. And of course, this degradation becomes even more severe if the malicious users attack more aggressively,
Higher, or pay, or if there are simply more of them present in the network.
Yeah, that really raises an important question for anyone running these networks. How much...
Critically, yes. The research demonstrates that detecting and then effectively dealing with these malicious users, either by completely removing their contributions from the fusion process, or more subtly, by giving their reports less weight, dramatically improves the overall CSS performance.
How much improvement? Back to the example.
In that same example we just discussed, where 3MUs drag Q down to 0.5, simply identifying and effectively removing the influence of those malicious users, using the methods we'll discuss,
Boosted the probability of detection Q back up to 0.7, 70%.
Okay, so not quite back to the perfect 0.8 of an all-honest network, but a huge improvement from 0.5. That's significant.
Makes sense. Now, let's dig into the effectiveness of this specific GMM algorithm across more diverse, maybe more realistic scenarios. You mentioned earlier it was tested with varying primary user activity patterns. What if the channel is mostly busy or mostly free? Does the GMM still work well when the H0 and H1 states are unbalanced?
That's a great question, because real channels often are unbalanced. The algorithm's robustness was thoroughly tested by varying the percentage of H0 samples, PU absent, channel free,
and H1 samples, PU present, channel occupied, in the simulated dataset. They looked at scenarios ranging from a 50-50 split to 60% H0, 40% H1, and even 80%.
Relative frequency of the two states. So it essentially adapts its internal model to how often the primary user is actually active. Makes it very flexible.
Very flexible. And the results across these different activity patterns are compelling. The figures in the paper, like figures 2, 3, and 4, consistently show that even with these varying proportions 50-50, 60-40, 80-20, the proposed algorithm reliably detects the malicious users.
Oh, by their low anomaly count.
Yes. In the example shown, the first 3 CSUs were designated as malicious.
And in all these scenarios, their calculated anomaly counts consistently fall below the dynamically calculated detection threshold, while the honest users counts remain above it.
So it works even when the two...
Okay, that's good to know. What about different attack probabilities? We talked about the attacker's dilemma: attack too little and you're ineffective, attack too much and you're easily detected. How does the GMM algorithm perform across that spectrum of attack frequencies?
Another critical test. The research shows the algorithm's effectiveness for attack probabilities. Us assuming I0 weighs a lie or 1 for simplicity in these tests, ranging from 0.3 up to 0.6.
So attacking 30% to 60% of the time when conditions are right?
Right.
And in all these tested scenarios, the proposed algorithm correctly and reliably detects the malicious users by their lower anomaly counts. However, there's a nuance.
If an attacker is extremely subtle, attacking only, say, 5% of the time, they might be missed by this method.
It's possible, yes. But then we have to ask, as you did earlier, why would an attacker bother being that subtle?
Right, if their impact is negligible.
Exactly. Malicious users generally don't attack with extremely low probabilities because their effect on the overall CSS performance would be marginal. Their efforts would be largely pointless, not worth the risk of eventual detection. They typically want to cause
significant degradation to achieve their goals, denial of service via false alarms, or gaining access via missed detections.
So the attacks that actually matter, the ones causing real harm...
So the more dangerous the attacker, the easier they are to spot with this GMM method. That sounds like a desirable
focuses on the most significant threats.
And how about scalability? Can this algorithm handle varying numbers of attackers in the network? What if there are no attackers? What if there's a significant minority, like 40%?
Good question. Scalability is key for real networks. The algorithm's effectiveness was demonstrated for the number
of malicious users, ML, ranging from 0, representing a completely clean network, up to 4, which represents a substantial 40% attacker presence in the...
Yes, crucially it did. When ML0, all the TSU anomaly counts were, as expected, above the calculated threshold. The algorithm correctly indicated no malicious activity in the network. This is just as important as detecting attackers. You don't want false positives accusing innocent users.
Absolutely. Avoids wrongly penalizing honest participants.
Okay, so it seems robust to PU activity, attack probability, especially for meaningful attacks, and the number of attackers. What's the overall detection accuracy like? If you average across these
scenarios, how often does it get it right?
The detection accuracy reported is highly impressive. As expected from the previous points, the overall accuracy of the proposed algorithm increases directly with the attack.
Yes, which, again, reinforces the idea that while very low probability attacks, which have minimal impact anyway, might occasionally be missed, the algorithm is extremely effective at catching the more aggressive and therefore more disruptive attacks that networks really need to worry about. It prioritizes detecting the attacks that truly matter for system performance and integrity.
This sounds very, very promising based on its own performance, but the real acid test often comes when you stack it up against other existing
algorithms out there. How does this GMM approach compare to what was available before? You mentioned the teach and more test earlier.
Right, the comparison is critical, and it's where the GMM strengths really shine.
The TM test, as adapted in reference 20 cited in the paper, makes its decisions based on data from single sensing instances. More crucially, it requires prior information about the exact number of malicious users, ML, in order to function effectively as a detector.
It needs to be told how many bad guys to look for.
Yes, you have to feed it the number ML. But this information, exactly how many attackers are currently active in the network, is typically unavailable to the Fusion Center in a real-world dynamic scenario.
You just don't know that number beforehand.
That seems like a major drawback for practical use, so GMM doesn't need that.
Correct. As we discussed, the proposed GMM algorithm can't...
The performance gap is stark, really highlights the GMM's superiority. Even when the TM test is given the correct ML information, its performance in detecting these soft Byzantine attackers is shown to be quite poor compared to the proposed GMM method.
How poor? Any numbers?
Yes, figure 8 in the paper compares their detection accuracy as a function of the attack strength. The proposed GMM algorithm achieves 100% detection accuracy at a relatively small attack strength of just 0.3.
So it catches even subtle manipulations.
Yes. In stark contrast, the TM test needs the attack strength to be cranked all the way up to 45, a massive deviation to achieve that same 100% accuracy.
45.
Okay, so GMM blows TM out of the water in terms of both practicality and no prior info needed, and sensitivity. What about other machine learning approaches that have been tried, like that one-class support vector machine, SVM, you mentioned from reference 24? How does GMM compare there?
The comparison with the one-class SVM method also favors the GMM approach significantly. The research found that the one-class SVM's performance in detecting these specific types of malicious users was very poor for the tested parameters.
Why poor?
Similar to the TM test, it primarily requires the malicious users to employ very high values of very large attack strength to be reliably detected. Again, this goes...
Yes, which, as we've established, is often unavailable and limits its practical deployment. So GMM wins on needing less information and being better at detecting subtle attacks compared to both TM and one-class SVM in this context.
Okay, so GMM is more accurate, more sensitive to subtle attacks, and requires less pre-information. That's a compelling trifecta. But what about the computational cost? Is it light enough for real-time systems, or is all this GMM processing too heavy?
That's another significant
advantage that really pushes GMM ahead for real-world deployment. The proposed GMM-based anomaly detection algorithm has a relatively low computational complexity compared to many.
Okay, and how does that compare to the others?
In stark contrast, algorithms like the one-class SVM, as described in reference 24, exhibit significantly higher complexity. The paper cites its order as something like O2M3 I1 plus L2 plus M2 plus MKI2. That M3 term can be very costly as the number of users grows.
Yeah, cubic complexity is usually bad news for scalability.
Definitely. Similarly, other clustering approaches like C-means, reference 27, also often come with substantially higher computational complexities
involving terms related to the number of data points in clusters.
So the implication is?
The implication is clear. This significantly lower computational complexity means the proposed GMM algorithm is much more...
That's a huge competitive advantage for practical implementation, because it's not just theoretically sound, but actually feasible to deploy. So, summing up the comparisons, GMM seems more accurate, more sensitive to the realistic subtle attacks, needs less prior information, and is computationally cheaper. It sounds like a clear winner.
Based on the evidence presented in this research, it certainly makes a very strong case.
Okay, so the GMM can detect attackers accurately and efficiently without needing to be spoon-fed information.
But what happens after detection? Is the only option to just remove the malicious users entirely from the network or the CSS process?
That's one option, certainly. Just ignore any...
detection threshold. It could lead to a continuous cat-and-mouse game where they keep probing the limits.
Okay, they adapt their strategy based on the defense.
Exactly. So this research proposes a more sophisticated and arguably more robust approach that goes beyond simple removal. Instead of just eliminating the NUs, the information gained from the GMM anomaly detection specifically, those anomaly counts, psi, for each user can be used to dynamically assign weights to each cooperative secondary user's reported energy data.
Weights, meaning some reporters count more than others.
Precisely.
It's a weighted fusion approach, meticulously described in algorithm 3 of the paper.
So you're not necessarily cutting them out completely, but rather strategically giving their input less importance, less trust in the...
Exactly. Now think back to our inverse logic. Who has a lower anomaly count C?
The malicious users, because they look too normal.
Right. So since malicious users have fewer anomaly counts, they will naturally be assigned smaller weights by this formula.
Okay, and the honest users?
Honest users with their higher and more naturally varying anomaly counts will receive higher weights, effectively creating more anomalies, up to a point, reflecting natural variation, means more trust, a higher weight. Unnaturally
Few anomalies means less trust, a lower weight.
That makes perfect sense. More trust for the reliable, honestly noisy ones, less for the suspicious to clean ones. So how does the
up the energies, but multiplying each one by its trustworthiness way first.
Precisely. This gives more importance, more influence on the final decision to the data reported by the users deemed reliable, honest, and systematically downweights the influence of data coming from suspicious, likely malicious users.
And what's the overall impact of using this GMM-derived weighted sum algorithm on the network's performance? Does it just recover partially like the removal case, or?
This is truly remarkable, and perhaps the most powerful and compelling outcome presented in the research.
When you look again at the receiver operating characteristic plot, figure 9 in the paper, comparing different scenarios,
Okay.
the performance curve for this proposed GMM-based weighted sum algorithm
Almost perfectly, yes. It's visually indistinguishable in the plot. This demonstrates something quite profound. The weighted sum algorithm, using these intelligently assigned weights derived directly from the GMM-Based Anomaly Detection, can effectively completely eliminate the negative effects of malicious users on the overall cooperative spectrum sensing performance.
That's incredible. So it's like the malicious users are still transmitting, still trying to deceive, but their deceptive signals are rendered completely
Powerless by the weighting scheme. They're effectively filtered out, neutralized, without even having to explicitly kick them off the network.
That's an excellent way to put it. Their influence on the final
diffusion schemes that might have been proposed before.
It significantly outperforms them, according to the comparisons in the paper. For example, compared to a weighted algorithm proposed by Gao et al., reference 21, this proposed GMM-weighted algorithm achieves a staggering 71.6% higher probability of detection, QD, and a false alarm probability, QF, of 0.1.
Huge difference. Why did the Gauss algorithm perform poorly?
Apparently, Gauss' algorithm primarily focused on removing only the single most malicious value reported in each sensing instance, which is utterly
insufficient when multiple malicious users might be present and subtly manipulating their reports. It's too simplistic.
Okay. What about others?
Similarly, the proposed GMM weighted scheme performs
So the GMM's ability to assess all users simultaneously based on their anomaly counts and assign nuanced weights seems far more effective against multiple coordinated or uncoordinated soft Byzantine attackers.
That appears to be the case, yes. It handles the collective impact much better.
The aha moment here is crystal clear then. This ability to not just identify attackers, but to adaptively mitigate their impact in real time, using weights derived from their own subtle statistical giveaways, and achieving performance that matches
An ideal attacker-free network that is incredibly powerful. It really feels like it redefines what might be possible in building resilient wireless network security.
We started by understanding the wireless landscape, the crowded spectrum, the need for dynamic access. Then we explored how malicious users can exploit the very cooperation that's meant to make these networks stronger.
Right, turning strength into weakness.
And then we unpacked a sophisticated yet surprisingly elegant solution using Gaussian Mixture Models for anomaly detection.
An unsupervised machine learning technique that cleverly leverages the subtle statistical signatures of deception, effectively turning an attacker's
own strategy against them.
You've seen how GMM can effectively identify these malicious users by noticing the peculiar two-normal statistical signatures. That fascinating.
This isn't just about obscure network protocols or complex math relevant only to, PhDs in electrical engineering.
Yeah, hopefully not.
The principles we've discussed here, things like identifying subtle anomalies in large, noisy data sets, leveraging robust statistical models for security purposes, and building inherently resilient systems designed to withstand intelligent adversaries. These are critical concepts across countless fields today.
Absolutely. Think about financial fraud detection, looking for
transaction patterns that are too regular, too clean, compared to normal, messy human behavior.
Or maybe medical diagnosis, identifying subtle deviations from healthy statistical patterns.
readings that don't fit the expected statistical model of the environment.
Yeah. Every time you connect wirelessly, every time you trust a digital system with your data or your safety, the ability of that system to identify and neutralize hidden deceit, hidden manipulation is absolutely paramount. We rely on this hidden layer of statistical security constantly.
It's becoming foundational to trust in the digital world. So what does this all mean for the future of wireless communication and maybe even beyond?
Well, that leads us to our final provocative thought for you, our listeners. If machine learning, and specifically tools like GMM
that can operate unsupervised and adaptively, can so effectively unmask these hidden adversaries and actively mitigate their impact in real time, how might this transform?
Maybe. And thinking more broadly, what other hidden patterns with subtle anomalies could GMM or similar statistical tools reveal in your own data, perhaps in areas of your work, your research, or even just your quantified self-data, in places you've never considered looking for these kinds of too normal or too clean signatures?
What secrets are hiding in plain sight within the statistics?
Exactly. Go forth and explore that.